Hello everyone. Today I'm going to talk about the representation of data in the computer in computing in general. And the first point that we're going to talk about is number representation. So how do we represent numbers in a computer? First, computers wanted to represent or be able to compute mathematic operations. So that's why I think we started thinking about how to represent numbers. So there are many different numeric systems that we use. We have the binary, the denary, and hexadecimal. Those are the three numeric systems that we use the most in computing. Now, the binary system obviously is the one we use the most because is the system that allows us to represent quantities or numbers or in general data by using two different states, right? And which means we're using base 2 for the numeric system. Two states, why? Because we can represent things like on and off, which is very easy to do in a circuit, right? In a electronic circuit. Or if we were talking about mechanical, we were talking about representing up and down. So in a machine might have been easy to represent up and down. And in other systems that we use now, we could make a difference between, for example, in magnetic tapes or in magnetic drives, we can make a difference between a space that is recorded and one that is not recorded, or one that has like a magnetic field on it and one that hasn't been affected by a magnetic field, or maybe this is positive and this is negative. So as you can see, binary system is very convenient to represent quantities because it's easy to represent opposite things or two different things in many different kinds of devices. So in binary system, then we need to represent two different states. When we're talking about the digits to represent those states, we have conveniently used 1 and 0, right? From our denary system that we use every day. So these are the two digits that we use to represent quantities in binary system. And in computing, those are the ones you use to represent basically everything in the computer. Now, that's the binary system, right? It's base 2. The one we are used to is the base 10, where we have 10 different states, 10 different states, and those states are represented by the digits from 0 to 9, right? That's our denary system. Now, hexadecimal system is another numeric system that uses base 16, which means that has 16 different states. So for those digits, we use the first 10 digits are going to be the same as in our denary system from 0 to 9. And then to start quantifying the rest of the states, we use these letters from A to F, right? So that's our hexadecimal system. Now, for us to understand, in order for us to understand how these two systems, the binary and the hexadecimal, represent quantities in the one that we are used to, we need to understand first how denary is made, right? So denary using base 10 is a system in which all the digits and the positions of those digits in a number represent different values. So in this number, 13,201.321, each one of these digits is representing a different power of 10. So after the comma, we start with positive powers, and before the comma on the left, positive, and on the right, negative powers. So this number represents 1 time 10 to the power of 4, right? 3 times 10 to the power of 3, 2 times 10 to the power of 2, and so on. And here we have 10 to the power of 0, which is 1, right? So this is 1 times 1. And then we start with the negative powers. So 3 here means 3 times 10 to the power of minus 1, which would be 3 times 1/10, right? So that's 0.30, right? So as we can see, the numeric system, the Denary numeric system, uses powers of 10, right? Because we have 10 states. Now, obviously, if we're talking about the binary system that uses 2 states, then we're going to use base 2. So the different positions in the number are going to represent powers of 2. Now, there is one representation where we use the comma as well, and we have the same way positive powers of 2 on the left of the comma and negative powers of 2 on the right. So this is 2 to the power of minus 1, 2 to the power of minus 2. So there will be 2 to the power of minus 3 here, right? And this is, if this is the comma, this is 2 to the power of 0, 1, 2, 3, 4, 5. Oh my god, I think I made a mistake here. But you understand the whole idea, right? We have here, if the comma is right here, so we go from 2 to the power of minus 1 to 2 to the power of minus 3, and we have 1, 2, 3, 4, 5, 6, 7. So we actually have the maximum here is going to be 2 to the power of 6, right? So according to that, this is all wrong. Sorry about that. Let's do it again. So what we have here is 1 time 2 to the power of 6 plus 1 time 2 to the power of 5 plus 1 time 2 to the power of 3, right? Because that's where the 1 is. I'm not going to add the ones that have a 0. And this is 1 time 2 to the power of 1, right? And then we skip this one. And then we move into this one. So it's 1 time 2 to the power of minus 1 and 1 time 2 to the power of minus 2, right? So this number should be 64 plus 32 plus 8 plus 2 plus, so that's for the whole part, plus 1/2 plus 1/4, right? So that should be 96, 104, 106. So this should be 106 dot 75, right? Okay. You're a very good mathematician, so I think you should understand that very easily. Now, for hexadecimal, the base is 16. So in base 16, we just use powers of 16, right? So this A3F is going to be 10 times 16 to the power of 2, 3. Well, the A represents 10 because, as I said, the first 9 digits in hexadecimal are the same 9 digits in Denary. And from A to F represents from 10 to 15, so A is 10. So this is 10, A is 10 to the power of 16, sorry, 10 times 16 to the power of 2, then 3 times 16 to the power of 1, and then this is F, which is 15, 15 times 16 to the power of 0, which is 1. So that's going to be our number, right? So A3F is 319 base 10. So that means that 319 in base 10 is equivalent to A3F in base 16, right? Now, talking about being equivalent, we need to understand how we can represent one number from one sister to the other. So from denary to binary, we know that we can use successive division. So I start by dividing the number in base 10 by 2, and then I take care of the remainder. I notice what the remainder is. So 102 divided in 2 is 51 with remainder 0. And I continue. And I keep track of the 0, and then I continue. 51 divided in 2 is equal to 25, remainder 1. 25 divided in 2 is equal to 12, remainder 1. 12 divided in 2 is 6, remainder 0. And so on and so forth. So I get this sequence of numbers, right? So to write the binary number, I take from the top, from the bottom where I got this, right? I need to divide the 0, the 1 divide, sorry, okay, here 1 divided in 2 is equal to 0, and remainder 1, right? That's where I stop. So what I have is 1 1 0 0 1 1 0, which is the same sequence going up. Now how can we test that this is true? So we take the powers of 2 for each one of these bits. Now each one of these is called a bit, right? And we see that if we add all those numbers, we get the 102. Now, how do we represent 102 from base 10 into base 16? So we do the same, right? We take 102 and divide it on the base. We get 6, and the remainder is 6. Then we take this 6, divide it in 16. The coefficient is 0, and the remainder is 6, right? So I can say that going this way, this number is 66 in base 16. So 102 is 66. Liu Liu, right? Now, how can I prove that this is really 102? Well, I can just multiply the digit times the value of the position. So in this case, it's 16 to the power of 1, 6 times 16 to the power of 0, which gives me 102, right? There is another way that we can do this. We can change from, for example, from binary system to denary by doing this. Let's take this number, the one that we know is already 102. So it's 1100110. I start by multiplying by 2. So the first number is 1, so I use 1 times 2 equals 2, right? Then I take this number and I continue with the next digit. In this case is this 1. So I add that 1. I take this 1 and put it here and add it. So it's 2 plus 1, 3. And then I multiply it by 2 again. I get a 6. Then I take the 6 here and I continue adding the next, which is 0. I get 12. 12 plus the next 0. I get 24 plus the next 1. 25 plus the next one, 51, 102 plus the next 0. And since I have no more numbers, I don't multiply, so this is the answer. That's another way to make a conversion. Now, between binary system, we know how to make a conversion to Denary system now, right? We can just multiply by each value, and then we know that, for example, this number 1111 is 255 in base 10, right? Now, what's that number in base 16? What we could do is make a conversion to Denary and then to hexadecimal, but it's easier if you just group the number in nibbles. So you take 4 bits, so 4 bits is equal to 1 nibble. And then you make the conversion between this number and Denary, and then you find the hexadecimal representation for that Denary number. So 1111 is 8 plus 4 plus 2 plus 1, which is 15, right? Then this 15 in hexadecimal is F, right? So this bunch of ones would be FF in base 16. So this number A03F41 in base 16 would be A, which is 10, 0, 3, F, 4, and I just missed one, 1. All right? Okay, guys, I'm going to continue later on with the next topic. So the next thing I'm going to talk about is how you represent different types of numbers. We know how to represent a positive number, right? Because that's what we just did. But how do we represent a negative number in binary system? So one of the first ideas that came when they were trying to represent negative numbers was to use a sign and magnitude approach. So in that approach, what you say is, let's just use 1 bit to represent the sign. So for example, the number in Einstein integers, we have this range, right? We go from 0 to 255. Let me just correct that. From 0 to 255. And that's because we have, that's the range for 1 byte. 1 byte is 8 bits, right? So we have from 2, the maximum number we can represent is 2 to the power of 8, which is 256. Or let's say we have 256 different combinations of 1s and 0s, which gives us the range from 0 to 255, right? These are 256 different numbers. So that's within sign integers when we have no sign. Now, for the sign and magnitude, what we do is we take the first bit and we use it for sign, right? And what we could say is that the 1, it's going to be minus, and the 0 is going to be plus, right? Or the positive. So in this case, -1 could be represented as 1, and then we use the remaining bits to represent numbers from 0 to 127, right? Since we have 2 to the power of 7, which is 128 different combinations of 1s and 0s. So this is the way that we would represent -1, and this is the way that we would represent +1. But the problem with this sign and magnitude is that then we would have 2 different representations for 0. We have 0 here and 0 here, and this is minus and this is plus, right? So we would have a minus 0 and a plus 0. So that's very inconvenient. That's why the sign and magnitude way of representing numbers is not used. So we use now the 2's complement, which is a better approach. So the whole idea about this was to use some bits for negative numbers and some bit for positive numbers, and then the result would be adding the result of adding those two sections, right? Now, to keep using the same values, so we can have some sort of correspondence with the previous or with the unsigned numbers, what they did was they said, okay, let's make the most significant bit a negative number, and then the rest of them are going to be positive numbers, right? So in that manner, we would have here, for example, let's just start with the most obvious one. What's the representation for 0? So 0 is just all zeros, right? If this is minus 2 to the power of 7, doesn't matter what the value is because they are all zeros, so the result here would be a 0, right? And we have a 0. Now, the representation for 1 would be the same as in unsigned, right? This is 1. Now, what would be the representation for minus, sorry, if this is minus 2 to the power of 7, since we're using 2's complement, minus 128 would be a 1 here and a 0 here, right? Because this minus 2 to the power of 7 is minus 128, right? Now, minus 127 would be to have a 1 here and a 1 here, because we would have minus 127 plus 1, right? So we can start decreasing by using these bits. If we start using 1s, we're going to go from minus 128 up to the 0. So what would be the minus 1? The minus 1 would be this, since we have all the positive values added plus the negative value. So we would have minus 128 plus 127, which would give us minus 1, right? That's 2's complement. It's a very smart way to represent negative numbers, right? Now, how do you calculate or how do you create the 2's complement representation of a binary number? Let's say that I have a 32, right, from base 10, and I want to make it binary. Then, well, using any of the methods that we saw, we can know that this is 32, right? This is equivalent to 32 in base 10. So now, how do I make a minus 32? Then the procedure we can do is, first, we're going to take the number 32 and we're going to find 1's complement. 1's complement is found by replacing all 1's by a 0 and all 0's by a 1. So in this case, I take 0 and change it into 1 and all that, right? So I have 1, 1, 1, 1, 0, 1, 1, which is the opposite, right, of this. That's 1's complement, and 2's complement is found by adding 1 to 1's complement. So I add 1, which is this 1 here, and then I just make the binary adding. So 1 plus 1 is 0 and 1 carry. 1 plus 1 is 0 and 1 carry. and so on and so forth. So I get this number here. Now, how do I know that this is minus 32? There are two ways. I know that the first position is times 2 to the power of minus 2 to the power of 7. So that's minus 128. So it would be minus 128 plus 64 plus 32, right? And that's 32. Another way to do it is I reverse the process. So I take the number that I got, which is in this case is the minus 32, right? And I find 1's complement, I add 1, so I find the 2's complement. So that means that the 2's complement of minus 32 is 32, right? So I know that the original number then was a minus 32. All right, so there's something else that we need to understand is how we can represent binary numbers, sorry, how we can represent digits using the binary system. And so we use the BCD or binary coded decimal. The basic idea is to take each digit and make the binary representation of that number using one nibble. So as you know, one nibble is 4 bits. 4 bits would give us 16 different options, but for the numbers or the digits from 0 to 9, we use only 10 of those 16 options, right? So that means that we're going to have 6 options or 6 combinations of ones and zeros that are not going to be used. And that's going to be a problem if we want to add numbers. So the way to correct the problem when you're, for example, when you're adding those two numbers, that representation, is to add that difference, to add that 6. So let's just try and do this operation. We have a 36, which is 3 and 6. We provide the BCD representation of that, which is just to take one nibble and represent each number. So this is 6, right? And this is 3. 96 is 9 and 6, right? Now, this is a good BCD representation. It's to take each digit and represent it in binary. So let's see if by adding in binary these representations, we can get the original result. So let's add these two 6, right? We have 0 plus 0, 0, 1 plus 1, 0, and we carry 1. 1 plus 1, 0, and 1 additional is 1, and we have that 1 carry. And 1 plus 0 plus 0 is 1, right? Now we can see that this number, if we take it back to a digit, it would be something like 8 plus 4, which would be 12, right? And we don't have a digit for 12. We have to use 2 digits, right, in our decimal system. So what we have to do here is correct the number because we have an overflow for BCD. In BCD, we have from 0 to 9. So if we want to represent a 12, we need to adjust the number by adding the difference that we had, the 6, right? This 6 is going to be added here. So if we add those two, 0 plus 0, 0, 0 plus 1, 1, 1 plus 1, 0, and 1 carry, 1 plus 1, 0, and 1 carry, right? We get this, which is the 2, and the carry, which is 1, right? Because 6 plus 6 is 12, right? So as you can see, if we correct, every time we get an overflow, like here, if we correct by adding 6 in binary, then we correct the problem. So let's keep doing the adding of that number. So we had, here we had, this is 3, 6, 9, 6, right? And we had here a 2, and then we have the carry here. Then we continue adding, so this is 1 plus 1, 0, and carry 1, 1 plus 1, 0, and carry 1, 1 plus 0 plus 0 is 1, and then we have 0 plus 1, 1. So we have another overflow here because this is, again, 12, right? Sorry, yeah, 12. So this is 12. We need to make a correction, but first we need to add the carry that we had before. So 0 plus 1, 1, 0, 1, 1. So we get here a 13. And we need to adjust that number. So we add the 6, 1 plus 0, 1, 0 plus 1, 1, 1 plus 1, 0, and carry 1, 1 plus 1, 0, and carry 1, right? Now, we don't have more numbers coming here, so we don't need to adjust this. We just need to represent the one that we have in the nibble. So in the end, what we're going to get is, we take this down, right? It's 0, 1, 0, 0. This is the result for this addition, so this is the one we get here, and this is the one that we carried, so we get the 132. Okay, so that's how you correct the BCD problem of when you're making operations, like math operations like adding, right? Now, we can do similar things for subtracting, which is just adding a negative number, but that's not part of the course and not part of the topics that we're going to cover in this video. So that's it about the representations of numbers. Now, for the representation of text, if we already know how to represent numbers and we don't know how to represent words, which is just a bunch of characters, right? Then what we can think is combine those two concepts and just try to make these numbers represent one character, right? Now, this is what we call a coding scheme. So we just have one number value representing a particular character. So there are two main coding schemes that we use nowadays, the ASCII code and the Unicode. The ASCII, or ASCII, is using 1 byte, and Unicode is using from 2 to 4 bytes. Right now we're using 4 bytes. Now, how does that work? So if we know that, for example, our character A, capital letter A, we want a number representing that. Let's say that we chose this 65, right? That 65 has a equivalent in hexadecimal and equivalent in binary, right? So in the computer, in bits and bytes, this would be the representation for character A, right? This number, this combination of ones and zeros. So with that idea in mind, they created first the ASCII code with 7 bits, so they had 128 different characters, right? But that's not enough for nowadays and for the languages that we have nowadays. So the next thing they did was to use just more bits, right? And then they created the Unicode. Well, there was UTF-8 first, then they moved to 16, and then they went to 32. This is the one we're using right now. And with 32 bits, we can have all the characters in all the languages and all the emoticons that you can think of or that we use now. So we can have one standard to represent all the different symbols that we use in our different languages, right? Now, one thing that you have in common is that the first 128 codes of Unicode are the same as ASCII code. Now, as you saw, this character A in binary is this number, in hexadecimal is this, and in decimal is this. Now, for just to have fewer digits to represent all these numbers, we use hexadecimal because, as you already know, it's a lot simpler to describe bigger numbers using a hexadecimal system. So the character A can be represented in this coding scheme. This means Unicode, and these are 4 hexadecimal digits. Now in UTF-32 we have 4 bytes, which is 32 bits, right? Right here we're just using 2 bytes or 16 bits, which is 4 nibbles, right? This number right here. So this representation is just looking for the first 16 bits. Now you can check in Unicode what are the different symbols that we use nowadays, and there is a catalog to check the Unicode in many different websites. One thing that is mentioned in our textbook is that in order for them to try to make a difference between the first 128 codes in UTF to be the same as ASCII, they used a convention for characters that needed 2 bytes. And what they say there is that for ASCII code, this would be the pattern, right? A bunch of zeros here and then the 128 characters. And that for them, in order to make a difference, they would, if they needed 2 bytes for any Unicode character that was not ASCII, they would use this pattern. But that is not the case nowadays, right? So this is just for historical reasons, and maybe I hope not. I hope this is not going to be in the tests, but for historical reasons, is something that I think it was important at some point, but I don't think it is anymore. I might have to check about this concept again, but I have seen the Unicode codes that we have, and they don't follow this pattern. So I honestly don't know if this is just because of their historical reasons or if they, in the standard, they follow this pattern. Now, you can check that in the additional material that I left for you to see. All right, guys, that's it for today. I'll see you in the next video session.